Okay, we are at section 32.2, resistors and AC circuits, and this is going to be pretty straightforward because there's no reactive elements on this. So let's share the PowerPoint, and you can see that they just have a simple circuit of a resistor and an AC source, and just very simple circuit. So if we apply Kirchhoff's law, we know that the delta V source plus the delta V across the resistor equals 0. That was Kirchhoff's loop rule, that the sum of the circuits equals 0. So the delta VR is equal to IR times the resistor, where IR is the current, and the so IR is equal to delta V divided by R, delta V being the source voltage, and we saw from the previous that delta V is equal to delta V max sine omega t. So delta V max divided by R sine omega t will give us the current, and that's equal to I max sine omega t. So I max is equal to delta V max over R, and delta V R is equal to IR times R. So we multiply, if we expand IR, we get that's equal to I max times R sine omega t. Now we use a device called Phasor diagrams, and Phasor diagrams represent the magnitude and the angle at any particular time of a signal, and the signal goes counterclockwise. Probably looked clockwise to it may have, counterclockwise from the zero, counterclockwise, and you see that the voltage and the current are in line for a resistor. There's no phase angle between them. We'll see with inductors and capacitors there is a phase angle, but with resistors there is no phase angle. We can see that the current and the voltage are in phase. That means that they simultaneously reach their maximum values and their minimum values, and their zero crossing values at the same time. And that's no surprise with a resistor. Let's take a quick test. Consider the voltage phasor in the figure shown at 3 instants of time. Choose the part of the figure A, B, or C that represents the instant of time at which the instantaneous value of the voltage has the largest magnitude. Well, remember, it's the square root of the sum of the squares, and in this particular case, it would be C. C would be the largest, would give us the largest magnitude, and sure enough, it's figure C. Now, consider the voltage phasor in the figure shown at 3 instants of time. Choose the part of the figure A, B, or C that represents the instant of time at which the instantaneous value of the voltage has the smallest magnitude. And that would probably be the one with the smallest angle, so that would be B. And sure enough, it is B. Now, usually these chapters end with a quick quiz, but there's a little bit more in resistors. If you look at a signal, you have a signal above the zero line, and you have a wave below the 0 line. And if you were to average them, it comes out to 0. But we know that it's not 0. We know that there's a if you were to put a resistor in an AC circuit, over time it would get warmer, so there is power being dissipated in the resistor. It's not 0. So we have a different method called the RMS, root mean square current and voltage. We know that IRMS, root mean square, is equal to the square root of I squared average. Now, if you look at the I squared, you notice that everything is above the 0 line. If you square I, everything ends up above the 0 line. Here on this one, you can see there's you have half as much time above the line as you have below the line. So I average here is equal to 0. But if you square it, you'll see that it's all above the line. So if you take this square root of I squared, let's read the box. The gray shaded regions under the curve and above the red dash line have the same area as the gray shaded regions above the curve and below the red dash line. So the IRMS is equal to Imax divided by the square root of 2. And that's equal to 0.707 Imax. The square root of 2 is 0.707. That'll be an important value throughout the remainder of this chapter. Now, the P average is equal to IRMS squared times R. And VRMS is equal to Vmax divided by the square root of 2. And that's equal to 0.707 Vmax. Now, meters like this are designed to measure RMS value. So right now it's reading 0. I've got it at 200. And I'm going to measure. Now, you need to be careful. I'm a professional, so I'm going to put this into a circuit here. And you'll see that we measure, I don't know if you can see that, it's 120 volts RMS. So the peak is actually about 170. If I were to have an oscilloscope and look at the signal coming, it would be a 60 hertz signal at 170 volts max, thereabouts, 170 volts max or 170 volts min. Now let's remove it out of the extension cord for safety. And so these are the values. The RMS values are the ones that we use to do a lot of calculations. We can use the max, but we quite often end up using the RMS. And I believe that ends the section on, yes, that ends the section on inductors. Next, I'm sorry, on resistors. Next, we'll go to a discussion of inductors.